So the project that we're working on is we're trying to make a new type of dispersant, a new platform of dispersants. And if you take traditional dispersants that are used in oil remediation or any kind of soap, that you use for cleanup, they all have what's called a critical micelle concentration, which means that the molecules need to be above a particular concentration in order to emulsify the oil. The problem with oil spills in the ocean is that when these emulsions, when this encapsulated oil gets to the infinite dilution of the ocean, these emulsions break apart and the oil re-slicks and you have to reapply the dispersant. And so what we're trying to do is we're trying to develop a new class of materials that don't have this concentration issue. And the way we're doing this, actually, there's a number of different kind of chemical and physical constraints that we have in terms of these types of molecules that we're making. And so one of them is that they need to be large enough so that they're not taken up through the gills of fish. So we're working with a toxicologist. Her name is Nancy Denslow. She's from the University of Florida, who's basically looking at the toxicity of these nanoparticle-based dispersants that we're developing on fish. So they need to be above a particular size. And we also want this characteristic where they don't rely on a self-assembly mechanism where you can have the material assemble or break apart, right? We want it to be a single molecule. So if we think about a molecule is typically 1/10 of a nanometer. So a nanometer is basically if you take a meter and cut it up into a billion pieces. And that's basically the size of a molecule. And so we're trying to make molecules that are 1,000 times bigger than that. And so the way we do this is we use a nanoparticle template. So we start with a silica nanoparticle. And of course, silica has the same composition as sand, like on the beaches. And then we can basically grow a polymer from this. And then we can do some chemistry with this polymer in order to basically link the different chains together. And then we can attach another polymer. And so what we want to do is we want to have one of the polymers that's going to encapsulate the oil and take the oil up into the core. And then another polymer that we're adding, which is going to give water solubility to the dispersant. So you need this so-called amphiphilic character, where you have one part that's hydrophobic, that really likes the oil, and another part that's hydrophilic, that likes the water. And so we're trying to make these molecules with these chemical constraints in terms of how having hydrophobic and hydrophilic components, but also these physical constraints where they need to be around 100 nanometers in size in order to not be as toxic to fish. What we can do then is once we grow these from the nanoparticle, we can digest the nanoparticle and then we have a core that's empty and can be filled by the oil. So, we've had a couple highlights. So one of the highlights we've had is that a lot of the original hypotheses we had in terms of materials that would be water soluble haven't really turned out to be true. And so the highlights are really developing new chemistry because of failed hypotheses that we had in the original proposal. So for example, one of the polymers that we use that's the oilphilic polymer, the one that's going to encapsulate the oil, is a polymer called polycaprolactone. And polycaprolactone is biodegradable, it can be remediated, right? So it's it comes from a biosource, right? So there's a lot of kind of green applications to that. And then the water-soluble portion, we hypothesized we could use what's called hyperbranch polyglycidol, which is kind of like ethylene glycol, like you put in your antifreeze, but then it's a branch chain. And so it has all the characteristics you'd expect for something that's going to be water-soluble. It's just like ethylene glycol. The problem is that the defined arrangement that you have in atoms doesn't allow water solubility, because the water isn't able to kind of go into these different crevices that you get from having a branch structure. And we completely didn't realize this at the start. So what we've had to do is we've had to really modify our approach and say, okay, well, first of all, can we do anything with these hyperbranch polyglycidol materials that we've made and are not water soluble? Can we impart water solubility to that? And then the other question is, can we use a different chemical functionality that might be better and more effective in terms of giving us water solubility? So to address the first issue, what we're doing is we're taking the polyglycidol, which are basically branch structures, and we can basically attach hydrophilic polymers to these. And they're kind of short hydrophilic polymers, right? So they give water solubility, but you don't need to add a whole lot in order to get a stable structure. And we found that just doing that simple modification gives us water-soluble particles, and then we've been able to do some uptake experiments and some toxicity experiments. The other thing we've done in terms of changing the chemical functionality is instead of using a branch structure like a tree, we're using just a normal branch structure like a comb. So we can make these comb-like polymers that have these water-soluble arms attached to them, and that's shown water solubility as well. So part of this is the synthesis. So this is done through my lab. It's also done through Scott Grayson at Tulane University. He's a chemist there. We do some of the physiochemical characterization, which is monitoring the oil uptake, looking at the colloidal stability of these dispersant molecules in water over time. That's done both in my group and also with Wayne Reed at Tulane University. And then what we've done is we've given some of these nanoparticles to Nancy Denslow in the nanotoxicology department at University of Florida. And one of the things that Nancy has found is that there is a toxicological effect in terms of incorporating oil-filled nanoparticles and looking at oil in the water-accommodated fractions and things like that. So there are some toxicity issues that we now, that we expected there to be more toxicity issues. The ones that we have are things that we can deal with, but we're getting some real quantitative information about how much safer these are compared with things like Corexit or just having water that's been ultrasonicated to form an accommodated fraction. So I think if I were to separate these two out, in terms of the Gulf of Mexico, one of our goals in making these dispersants is to try to make a material that's not just applicable to saltwater situations like the Gulf of Mexico. We also want these to be applicable to freshwater situations like in rivers. So it turns out that if you look, that there have been many years where the number of gallons of spilled oil through kind of mishap and negligence in a river and a freshwater type of environment exceeds what's seen in saltwater, where typically you see something more catastrophic, but you don't see kind of day-to-day oil spills like you do in a river. So we're trying to make a material that doesn't have any charges on it so that there's no salting effects that you have when you apply this. So yes, it's applicable to the Gulf of Mexico, but we're also trying to incorporate a broader applicability for these materials. From a scientific standpoint, there's a lot of kind of fundamental questions regarding what happens when we take these these chain-like molecules, and attach them to surfaces. And one of the things we've found is that when we grow these polymers, so we're basically growing polymers from these nanoparticles. So we start with a particle that's silica, it's basically sand, and we grow hairs, right? And these hairs are the polycaprolactone, for example. And from a fundamental standpoint, one of the things we found recently was that the length of the polymers that you have that form the brush around this nanoparticle is strongly dependent on the chemical conditions under which you do the polymerization. What I mean by that is as these chains grow from the nanoparticle, there's a lot of side reactions. These are what are called transesterification reactions. And it happens when you have a growing chain that can attack a chain that's also part of the brush that's adjacent to it. And what that does then is it creates these brushes where all the different lengths of the hairs are different, right? So if you can imagine getting a haircut where they can make each of your hairs a different length, right? And you think about what would happen, what your hair would look like in that case. And it turns out that with these polymers grafted to these nanoparticles, that the shorter chains are able to kind of adopt a more close-packed geometry, which forces the longer chains to extend further out. So it even has an effect, on what's happening at the interface of these nanoparticles in terms of what the individual chains are doing. Now that has that has implications in terms of how well you're going to be able to fill the nanoparticle with oil eventually. Yeah, and again, what we're trying to do is we're trying to develop a broad platform that's going to be applicable to both freshwater oil spills and also saltwater oil spills. So we're using uncharged components so that we don't have any salt effects. And then we're trying to look at the toxicity in both saltwater fish, which is what we've done primarily so far, but then we're also going to be merging into some freshwater fish and looking at the toxicity studies with those.